Hello, folks. Welcome to Rational Science. What are we going to do today? Well, we're going to do motion today. And by the way, I'm on the road, and so I'm carrying my computer with me. So if the sound does not come out right, well, I can't help that too much. I don't have a very high tech here. I have just a little camera. I turn it on. That's it, and I get whatever sound it gives me. Anyways, we're going to do motion today. And, the question is whether Father Universe moves. We're going to argue today that every atom in Father Universe, only has location. He looks at himself. Father Universe looks at himself, says every atom simply has location. And we say, yeah, but I saw you move because every atom moved to another location, then to another, and then to another, and then to another. And Father Universe doesn't know what you're talking about. What the hell? What do you mean? I only have every atom only has location. Every time I look at it, only has location. And so maybe the problem is that we're not communicating with Father Universe. We are all living entities, and we have this memory, this device that records, previous locations. And maybe that's the problem. We remember the previous locations, and so we see this movie. But Father Universe is not a movie. Father Universe is a photograph. He only has location. Anyways, we're going to go into that. Then we're going to answer a couple questions regarding the rope model. But before we can before we can talk about Father Universe, whether Father Universe moves or has location or whatever, we need to look at another problem, a more fundamental problem, and that is, what is science? What is physics? And we seem to have already a major problem understanding what physics is and what science is, okay? What I'm going to do today, a lot of people won't like it, is I'm going to raise the whole board, okay? Everything that's been done from today to the past, to the days of the Greeks and even before, we're going to raise it completely. It's all been irrational, okay? And it's been irrational in great measure, because we have not defined what science is, let alone what physics is. We don't seem to know what physics is. And that's the argument today, at least the introduction to the argument. Okay, so let's start with this. This is, you look up the word science in the Google, you Google it, and you get this AI, which lately is very popular. Everybody consults the bots, right, to see what the official versions are of words or whatever they're looking up. It turns out all these bots, you have to keep this in mind, all the bots were programmed by mathematicians. And unless you understand that, there's a lot you're going to miss, okay? So make sure you understand that all the bots, the GPT and whatever, all these are programmed by the mathematician. They're putting the words into the bots. Okay, so that's important to understand right off the bat. But this is when you put up the word science in Google, you Google it. That's what you get. Okay, here it is. It says the AI. Okay, and it says science is a systematic way of what? Studying. No, in science, we do not study anything. You can study all day long, all week long, all month long, all year long, and it doesn't mean you understood. Okay, so studying is not part of science. We do not study in science. It's not an ongoing process, and that's where we already start failing. Any definition of any discipline within science that begins with the word study or studying, it's already, irrational, because studying doesn't guarantee understanding. And then you have knowledge, because science, derives from the word know, if you look it up. And this is our ancestors who screwed that one up badly. Science is not about knowledge. Knowledge is simply more firm, more fanatic, belief. Okay, people who believe something, well, they believe it. But people who know something, hey, you can't change their minds because they know it. Their belief is very, very strong. So knowledge is just stronger belief. And so we don't pay attention to knowledge in science, in genuine science. Okay. The big one there is testable hypothesis. What do you mean a testable hypothesis? I thought a hypothesis was an assumption. You don't test assumptions, you concede them in order to understand the theory that it underlies, right? But let's continue. We have predictions. No, we don't. We're not astrologers. We don't predict anything in science. Science has to do only with the past. We explain things that happened, not predict things that haven't. Okay. Evidence. No, we don't use evidence in science. Evidence is what is used to persuade, to convince, to convert someone, to recruit them, right? And so we don't use evidence in science at all. That's got to do with religion. It's got to do with persuading, having people change their minds, right? So we don't use evidence at all. We don't observe. We don't gawk. Why? Because observation doesn't mean that you understood. You know, and people say, well, how can you know what you're talking about if you don't observe first? Well, you know, you can have hypothetical situations. It turns out our blind sage, has never seen, and he was quadriplegic as well. He doesn't see or can't touch anything, but you explain the situation to him, or you describe a situation to him, and he's got to answer the question, the mechanism, the cause. Okay, so you don't have to observe in science. And the problem with observation really is that they turn observation into a proof, into evidence. You know, they say the particle went from here to there. Well, how do you know it was a particle? Did you see it? And they say, we observed. Now, you did not observe a particle. You're making an assumption that it was a particle. That's the way it works in quantum mechanics. They did not observe any particles. They make an assumption that they're working with particles. So the word observe or observation are turned into weapons to try to force it upon you that they did see it with their eyes. Are you going to challenge what they saw with their eyes? No, they did not see it with their eyes. And measurement has to do only with mathematics, with mathematicians. We do not measure anything. Science is about something else. It's about explaining, not about measuring. Okay, you measure the table. Does that mean that you're a scientist because you measured a table? So this is where the problem is, that a lot of these words are used as weapons against the person who's trying to understand. Okay, and they say, "Whoa, we observed, we made predictions, and the prediction came true because we measured," and so on. All those words have nothing to do with science. That's why we're erasing the slate completely clean. Okay, we're saying none of that has anything to do with science. Okay, just in case, here's the Science Council. It has essentially the same words. So, it's not like I just picked one out of nowhere. All of them have the same idea of what science is. They're talking about knowledge, evidence, predictions, experiments, evidence. None of that has anything to do with science. Okay, all the words that are underlined there. Okay, so, but I'm worried about this testing the hypothesis, the one there in the center. Hypothesis, do we test hypothesis? Is that what we do in science? Okay, let's find out what a hypothesis is according to these people, why they're going to test it. Okay, and here we have this this definition according to the official version out there. Hypothesis, a proposed explanation for a phenomenon. So we have explanation. And what is an explanation? A set of statements usually constructed to describe. So is an explanation a description? Well, what is a description? It's a characteristic and aspects to form a mental picture, impression, or understanding of something, right? And so the issue here is that, no, a hypothesis is not an explanation, because an explanation is not a description, and a description is not a hypothesis. In other words, all the is not an explanation. In other words, what they're doing is going around in circles here. They say hypothesis is an explanation, which it ain't, right? And an explanation is a description. And so we need to distinguish what these words, the differences between these words. What, we need to define what these words mean. Okay, and when you look it up, it says the following: it says a different meaning of the term hypothesis. This is out of the wiki, by the way, is used in formal logic to denote the antecedent of a proposition. Thus, in the proposition, if P, then Q, P is what? The assumption. It's an assumption. And if you look at it further, you'll see it's a supposition. So assumption supposition is not an explanation. And so they have contradictions because they're defining it as an explanation, hypothesis, right? When later on they describe it as, or define it as an assumption or supposition. And yeah, supposition, assumption, they're not explanations. You make an assumption so that people can follow your theory, founded upon that assumption. That's the way it works. And if you go back to the Greeks, here you have, the Greek, this is again out of the wiki, the Greek natural philosophy of classical antiquity. Formal attempts were made to what? Provide explanations. That's what they were trying to do. They were trying to explain. That's what science was. It was an explanation. They were trying to explain how this universe works. Explanation of events in the physical world based on natural causes. Yeah, they were trying to explain causes. That's how science started out. That was the idea. People want to know why things happen, how meaning why the universe works the way it does, the causes, the mechanisms. We want to understand why, this thing falls to the floor. That's what we want to understand. That's a cause, that's a mechanism. And that's not what we have today. In fact, we have no mechanism whatsoever for any phenomenon involving invisible, intangible mediators. That's where the problem is. That's what we have to solve. And some people say, science is not about explanation. Science, meaning mathematical physics, right? Which is an equivalent of science in the minds of many people. It's got to do with descriptions, with mathematical descriptions. We measure, we have an equation, we're done. We're done with mathematical physics. And, here are some testimonies, if you want to listen to them. Here's one from a professor in Pennsylvania, and he says the following. He says, science doesn't explain, science describes. So the first thing you notice there that there seems to be a difference between a description and an explanation. The second one is he's stating that science is about descriptions, not about explanations. So meaning mathematical physics, because that's what he is. He's a mathematical physicist. And so the question is, is that what science or mathematical physics is supposed to do? Physics, is it supposed to just describe and say, look, this is a description, mathematical description. We tell you how, not why. Okay, that's what's at stake here, right? Okay, so there you have one testimony, a fellow who works at a university, right, or at least did work. Here's another testimony. This is from good old Nobel Prize Richard Feynman. He said the following. He says, we choose to examine a phenomenon, the double slit experiment, right, which is impossible, absolutely impossible to what? Explain. He's talking about explaining it, okay, in any classical way. Nobody can give you a deeper explanation. He's talking about explanation. And as he says, of this phenomenon that I have given you, that is a description of it. That's all he can give you. He can give you a description, a how. He cannot give you an explanation, a why, the cause. Okay, so we're distinguishing between explanation and description. That's the first issue. The second one is they say we don't do explanations, we do descriptions because, as he says further down the line, he says theoretical physics has given up on that. In other words, the mathematical physicists, they cannot explain anything. They've given up on that. They've given up on trying to explain. And so they've reverted. They changed the rules. They changed the purpose of physics. And they say, from now on, we're just going to describe. We're no longer going to try to explain. Okay? And so, we have a problem because there's a disconnect between what physics started out with, what science started out with, which was trying to explain things. And these people are now saying, hey, we've given up on that. We don't do explanation, we do descriptions. Okay? And so here I can give you my version of that. Here it is, the scientific method and the science that we propose here, what we call rational science. Rational explanations, that's what science is. Okay, so if you need to have a rational explanation. If it's irrational, it's not an explanation, let alone science. Okay, and so what we get out of mathematical physics are irrational explanations. That's where we stand today. All we get is irrational explanations, and people are kind of sick and tired of that, and so they kind of tune out and they don't watch a lot of this stuff. They've become disillusioned, I guess, with science because all they get is black holes and dark matter and dark energy and Big Bang particles at two places at once and all this other nonsense. And they say, look, I don't want to listen to that anymore. It doesn't make any sense to me, right? So they tune out. And now we're saying science is rational explanations. That's why we have to erase the board completely because somewhere we went wrong, okay? Somewhere we made a wrong turn in the history of science, okay? And there you have, what is a hypothesis? It's not an explanation, not a tentative explanation. It's identify objects. You have to have objects, definitions, and the initial scene. Those are assumptions, okay? And that's what you're going to base your theory on, which is an explanation, a physical interpretation, okay? So that's what we're proposing. That's why we're called rational science, because we distinguish what we do here with what the mathematicians do, which is irrational science, mathematics as we call it, which is, they don't even have a hypothesis. They don't have assumptions. They start out directly at a theory and say, let me tell you my tentative theory. Theory of what? I haven't seen, the objects yet. I don't have your definition. I don't have the initial scene. And they already start in the middle of the film giving you their theory, their explanation. And they say, well, it's a tentative explanation, so we call that a hypothesis. Once we prove it, or we have more evidence, we have more measurements, more equations to back it up, then it becomes a theory. And when the democracy, sets in and most of the mathematicians believe in the theory, it becomes a fact. And they shove it down your throat. That's science in a nutshell for you today. And we're saying all that is completely misconceived. It's got nothing to do with what science is supposed to be, what physics is supposed to be. Okay, so here we have the differences between the mathematical method, mathematics, and the scientific method, what we propose. You can see the hypothesis is totally different. The hypothesis in mathematics is tentative explanation. There is no provision for assumptions. They say we observe, we hypothesize, they already have a theory, then they start making predictions, I guess consulting the crystal ball or reading your palm, I don't know what they do. Then they do an experiment, they measure, they formulate an equation, and then they start trying to prove to colleagues, right, through what they call peer review, right? The colleagues try to falsify your theory because they have a better one, or they have an alternative one, or they're skeptical about your interpretation, I guess. And if you happen to convince them, then you win a prize, they all vote for you, and you go on the talk circuit. Yeah, none of that has anything to do with science. That has to do with convincing, persuading, recruiting people to your way of thinking. No, the scientific method is objective. It's a hypothesis, is made up of the assumptions. The assumptions include the objects, for the purposes of physics here, right? The objects that you're going to use in your theory, the definitions, hopefully they are rigorous, right? And the initial scene. You start at the first frame of the film, okay? Then you explain your theory, okay? The physical interpretation. Okay, so you can see there's a difference between them. So we're proposing something totally different for science, let alone physics, which is a branch of science, right? Okay, so there's one person out there in the Stack Exchange, one of these places where mathematical physics spreads its word, okay, the Stack Exchange. And a fellow says the following. This is a lot of mathematicians have the same way of thinking. Something worth noting. Science never describes the true reason why something happens, meaning explains, right? He's using the word describe when he means explain. It concentrates on what? Predicting the effects of what happens. Okay, so they're going to predict, and I guess that's a description, but he's talking about explanation. Okay, because he says, when one asks science why, meaning explanation, right, we answer by showing a deeper and more powerful model, which is a description. A model, unless you explain the cause, so far you only have a description. Okay, if you want the real reason, meaning cause for gravity, right, not reason. Reason is what is purpose. It's part of philosophy. Why someone does something. That's not the case with object, with things. In the case of things, we don't use the word reason or purpose, which is something which belongs to humans and to living entities. We use the words causes and mechanisms, which are the words appropriate for physics. Okay, so we're not talking about reason for gravity. We're talking about the cause of gravity. And turn to philosophy or religion. They believe causes belong to philosophy, religion, ontology, any of those semantics, right? They'll dare to try to answer such ontological questions. And is this guy right? I mean, is this what science is supposed to be? Science is supposed to be just descriptions, predictions, no assumptions, right? And no explanations or irrational explanation. You don't like my explanation, go to philosophy, go to ontology, and they'll try to answer your question. Is that how science is supposed to work? Is that what physics is supposed to be? Here we have, this thing. It's a straw. Right? Straw falls downwards, and that is the cause of that is a philosophical question. It's not a question of physics. Does that ring a bell to you? Is that correct? Does that sound wrong? Is there something wrong with that? Okay, so let's find out what they do today. Here you have one fellow. His name is Neil deGrasse Tyson. He's a famous showman, right? He's a so-called physicist, really a mathematical physicist, a mathematician. And what he does is he does explanations on his show. And so they asked him, I think it was on Joe Rogan's program, and he asked him, what is gravity? Can you explain gravity? Can you explain the cause of gravity? Why? Right? Not describe how. We mathematicians can do that. Can you explain why, the cause, the mechanism of gravity? How Father Universe does it? What's the mechanism? What's the trick, right? And this is a summary of what he says. He says, science can describe why gravity works, not why, how. So he's using describe to say why. Okay, he's confusing description with explanation. Why has to do with explanation, describe has to do with how. Okay? In mathematics, we describe how and believe we understand why. That's where the problem comes in. He says the how is a why in the religion of mathematics. Okay? Mathematics, how is equal to why. Mathematicians describe how gravity works. Okay? Gravity, what is it? Curvature of time. Called space-time, but it doesn't matter. When we put curvature of time so that people are aware that these people are saying they're bending time, if that makes any sense to you. Okay? And because when you say space-time, people say, well, maybe it's an object, four-dimensional, I can't imagine, okay. But when you say just time, then it shocks people. It hits them in the eyes. And what do you mean time? How do you bend time? And that's what they're saying. They're bending time. And but that's an explanation. That's a physical interpretation when you say, I'm going to bend something. Now you're giving a physics. Now you're talking about how. You're not saying, I measured, and this is how many meters, how many pounds. this was the distance, this is how much time. We're not saying that. We're saying we're bending something. Now we're talking about physics. Now we're talking about a physical interpretation. That's no longer a how, now it's a why. Okay? And here they go back and forth with all these things. And so he's talking about a cause, a mechanism, a why, an explanation, a physical interpretation. Right? So why does matter curve time? Rogan asks him, and he says, we're still working on it. What does he mean by that? He puts it off. He puts the question off. He says, don't ask that question anymore. We're working on it. And so he never answers the question. The question is, why, what causes gravity? And he says, it's curvature of space-time. Well, what compels, these number lines to bend? And then he said, we're working on that. No, they're not working on anything. There's no way you can answer because he just gave an irrational answer. That's why. That's the purpose, the reason behind that. He gave you an irrational explanation, and when you call his bluff, he says, we're working on it. Sometime in the future, we'll give you an answer. No, they're not working on it because mathematical physics, does not work on whys. So they will never give you an answer. And then he comes into another show and says exactly the same thing, and so on and so forth. Okay, so we've got a problem with what these people are doing, giving this type of information to the public. Okay, that's where the problem is. And here he is, listen to his own words. It's not like I put words in his mouth. You're going to listen to him now. Okay, so this is what he says. Okay, here goes. Listen carefully.
Science can describe how gravity works, but can they describe why it works? So this is the how-why duality here. In science, if we can describe how something works and predict its future behavior, we claim to understand it and we move on. There's a point where it's not especially productive to continue to think about the world that way. When you understand the how enough, are tantamount to having answered the why question. I can describe what gravity is doing. I even have a mechanism for it. Gravity really is the curvature of space and time. Movement of matter on that fabric of space and time, we call gravity. Why does matter and energy curve the fabric of space and time? And I don't have an answer for that. Why does matter and energy curve space and time? Okay, that's a frontier. We're still working on that.
So, did you understand the cause of gravity, the mechanism of gravity? No, in the end, he has no answer. He's telling you it's the curvature of space-time, curvature of time, the bending of time. It's an irrational answer. So they ask him, what bends time? How can you make sense of that? He said, we're working on it. Ask me that in 100 years. He's putting it off. He has no answer. But the important part here also, in the background is that he's trying to answer a why question. He says they did answer a why question. It's a description in which they turn into a why, into an explanation, into a physical interpretation, and that the mathematicians are satisfied that they answered the why question with their description when they didn't. Okay? And so they go back and forth between this how and why. And they work on the hows. They say they know why, and when you question the why because it's irrational answer that they gave you, they say, we're working on it. Put it off into the future. Don't ask that question again, please. Okay, but here we have another fellow. His name is James Beecham, and he tells you that these people do work on whys or are interested in whys, okay? Just like, Richard Feynman said, they gave up on the whys, but they're interested. That's what physics was all about the whys, okay?
What causes gravity? So physics, as you know, this is the type of question, what causes gravity? This is the type of question that keeps physicists up at night. Because physics is, among other things, as you know, the search for mechanisms, the reasons or explanations for why certain things happen the way they do.
So, do mathematicians, meaning the physicists, who call themselves physicists, are they interested in the whys? Of course they are. That's what physics is about. Why? Not the math. It's the physical part. How this universe works. What is reality? How does reality work? We want to understand how gravity works. We want to understand how light works, how magnetism works. That's what we want to understand. And these people, as Richard Feynman says, they've given up on that. They want to understand it. They don't understand it, so they give you a description in lieu of an explanation. Okay, that's where the problem is. Okay, but what's the way to destroy their argument? This notion that mathematicians, physicists, right, as they call themselves, we only do equations, we only do numbers, we do calculations, and that's our realm. And so don't ask why, don't ask for physical interpretations, go to philosophy for that. Well, that's nonsense. And here's proof, evidence, okay? Let's prove it. Proof and evidence, that's what these people believe in. Okay, so here, let's provide evidence. Yeah, you have all these people. You have Tyson there, Sean Carroll, Carl Sagan, Brian Cox, Brian Greene, any of them, Hassenfelder. What do they do every day? On their shows, on their documentaries, on their interviews. What do they do? Do they do equations? Do they put an equation there and say, look, this is the equation so-and-so, and this is equal to this other thing, and if you take, the limit of this, is that what they do? Do they put equations on their shows, on their documentaries? Do they even do experiments? Say, let me show you an experiment that proves my theory. No, what they do 90 to 99% of the times, maybe 150% of the times, right, is physical interpretations. They're doing explanations. They're trying to explain to you how this universe works according to the mathematical physicists, mathematicians, right? They're trying to explain to you. They're giving you physical interpretations all day long. I mean, go to any other sites and you will not find equations, because if they did put equations, nobody would watch them. They wouldn't have a single hit. Everybody would run the other way and say, no, I got better things to do. Okay, so all these people do physical interpretations all day long. Then when you say, look, give me a physical interpretation for gravity, oh, we don't do that. We do equations. Well, we got a contradiction, because that's what these people do every day. That is their line of work. All these so-called physicists who are online, who are trying to convince the public that they're correct, that they're right, that their theories are proven facts, right? That they know. What they do is physical interpretations all day long. That's 100% of what they do. But then they deny it when you say, well, you do physical interpretation, and you tell me why, what causes gravity to work or magnetism to work. Oh, we don't do that. Go to philosophers. Well, if you go to the philosophers, I mean, are they the people who are supposed to answer these questions? Why did the physicist, the mathematician, why did he attempt to answer a why question, a physical interpretation type of question, if later on he's going to say we don't do that? I mean, is he a philosopher? Does he have a degree in philosophy? Is he an expert in philosophy? Why are they giving you physical interpretations if it's not part of their line of work? If then they send you over to the philosopher and say, go ask them. Turns out you go to the philosophers and they get their cues from the mathematicians. I mean, go to Stanford Encyclopedia of Philosophy, right? And any analysis they make of things related to physics, they all come from the mathematical world. And so the question is, they try to interpret and they give the same interpretations as the mathematicians. So there's no differences between them. And they tell you it's irrational, we don't understand it, but that's what mathematics tells us. So they all give you the same answer. So whether you go to a philosopher or the so-called physicists, the mathematicians, you always get the same answer. And so who do we have to go to get an answer to the question of why? What causes something to happen? And the answer is there's no one out there today. Okay? Mathematical physics does not give you why answers, rational why answers. And the question is then whether mathematical physics has anything to do with physics, let alone with science. I mean, is it science? If science is rational explanations, mathematical physics has nothing to do with science, let alone with physics. That's our position here, right? And so here we have a definition of physics. What is physics from the Wikipedia? It says physics is the scientific study, again, study, we don't study anything in physics, of matter, its fundamental constituents, its motion and behavior through space and time, and the related entities of energy and force. Physicists generally, this is under the physicist article in Wikipedia, generally are interested in the root or ultimate causes of phenomena. So if they're interested in causes, it is part of physics. But they have these contradictions. They say they're interested in causes. Then when you talk to a mathematical physicist and put him against the ropes and begin to pummel him because he gave you an irrational explanation, it says, we don't do causes. Go to the philosophers. So we have this constant contradiction between, what is physics? It's like they don't know what the subject matter of physics is. Here it says that physics deals with causes. Then the other one says, we just study, we do ongoing work, we do descriptions, we do math equations, and we don't do causes. And then for physics, you look it up, it says causes. Okay? And it says, theoretical physicists specialize in modeling physical systems to rationalize, explain natural phenomena. So do they do explanations? Do they do causes? Do they do physical interpretations? Or are they just going to describe mathematically what is physics about? And so down at the bottom, we have little old me there. Science, rational explanations. Physics, rational explanation, which is a branch of science, right? Rational explanations of causes and mechanisms. Now we finally have a definition of what physics is. And of course, those two definitions, they exclude all of mathematical physics, especially quantum mechanics, general relativity, and string theory. None of those have anything to do with science, let alone with physics, because they don't have any rational explanations. Okay? So here are my conclusions for this segment, which is the introduction. Conclusion: mathematicians who label themselves as physicists have yet to define the subject matter of physics unambiguously. Do they do explanations? Do they do physical interpretations? Do they do causes or not? Okay, that's the question they have to answer. They have to answer that up front before they begin to talk in their programs, in their interviews, in their documentaries, because that's what they do in all those places. They talk about explanations, okay, about physical interpretations. Celebrity mathematicians, what they do, most of their shows, 90 to 99, say even up to 150%, they're explanations, physical interpretations. Okay, that's what they do in all their documentary shows, interviews, etc. When confronted with their irrational physical interpretations, the mathematicians dismiss explanations as philosophy. Go to the philosopher, don't ask us. So when did they attempt to do explanations? These are not part of their job descriptions. If it's not their line of work, why are they giving you explanations on their shows, on their, during their interviews and in their documentaries? Do they have degrees in philosophy? And if not, then they should stick to math, numbers and equations, and leave physics, alone, right? Who should answer such qualitative questions if not the noble discipline of physics? Okay, so we have a problem because right now we have no definition of what physics is, no unambiguous definition of what physics is. Does it do, especially, does it do causes, does it do physical interpretations or not? It's black or white. Either they do or they don't. Okay? If they do, then they have to come up with an explanation, a physical interpretation for gravity, for magnetism, for whatever. If they don't, then why did they attempt it in the first place? Why is it that that's what 100% of what they do on the, in YouTube and all the popular sites when they talk to the public? And are they, philosophers? Are they experts in philosophy if they dismiss that as philosophy? I mean, why are they doing this if it's not their line of work? And if not them, who? That's very simple. So those are the questions we have to ask any mathematical physicist, mathematician, right? Before he begins to talk. That's got to be settled first. Okay? Okay, let's move on to now what we did these last couple weeks, right? And we've been doing, going through the motions of finding out, especially static concepts versus dynamic concepts, and whether Father Universe, all the atoms in the universe, whether they belong to the first set or the second set. Okay? And so we begin with what I call the golden principle of physics, okay? Foundations of physics, okay? What are they? The golden principle is physics requires an object. You can't do physics without an object. If we erase all objects in the universe, there's nothing there, nothing is happening. What are you seeing? What are you imagining? What are you visualizing? What experiment can you run if experiments are part of science? I mean, nothing's happening because there's nothing there. So the first thing you need in physics is an object. You can't do physics without an object like the mathematicians do. They do action at a distance, which is the scientific version of black magic, of witchcraft. It's voodoo physics. They say action at a distance, meaning there's no mediator. So they're doing physics without mediators. It's even worse. They use concepts. They say that it was the energy, it was mass, it was the field, it was the wave. No, those are concepts. You can't substitute an object with a concept, mathematical concept, and say, I explained it. And that's what they're doing. They're giving you physical interpretations using abstract mathematical concepts. Okay, so the first word you need to define in physics is the word object, because physics requires an object. You can't do physics without an object. Okay, so we talked about that a couple weeks ago. Okay, let's move on then. What's next? Next one is the word space. If you define what something is, you have to define what nothing is as well, because we have all these somethings and nothing out there. Okay, that's the universe. The universe is made of objects, the things, and it's made of nothing, which is the other half. We can call it not really a half, a little more than half, but we're talking about this contrast between objects and nothing. Okay, and so I like to put it this way. So something, objects, is a synonym of nothing, okay? An antonym of nothing. Something and nothing are antonyms, okay? And so only then can you make sense of these two words. What something is, what nothing is. Something, that which has shape. Nothing, that which doesn't. Here, very straightforward, okay? Is space infinite? No. Infinite is an adjective. It can only be used with objects with the somethings. You can say chair is green. You can say, that the rock is big, but you can't say that love is big. Not in physics. Okay? You can't use adjectives to qualify concepts in physics. And when you say that space is infinite, you're using infinite, an adjective, to qualify a concept, nothing. No, nothing is not infinite or finite. Okay, so you can't say space is infinite or universe is infinite, because universe is also a concept. There's no thing called universe. Matter is the thing part of universe, and space is the nothing part of universe. Okay, universe is matter and space. Okay, so both universe and space are concepts. You cannot say the universe is infinite or space is infinite. Those are irrational statements, because you are using an adjective to qualify a concept. That's irrational in science. It's irrational in physics. Okay, and so, we have, here we have, again, my straw. I think it's better than the pens. I keep breaking all these pens, right, when I do this. You let go of the straw, and it falls downwards, right? And so people say, well, there's nothing here and there's nothing there, so it's action at a distance. Somehow, apparently the Earth is attracting by some magical means the straw downwards. Okay? Now, there's no magical mean. Here we'll have good old Richard Muller, professor at Berkeley, and says if you have the Earth, there's a big mass here, and you have you with your little mass here. Every atom on the Earth is pulling on every atom of you. you're also pulling on it. Let's repeat that because maybe a lot of people didn't hear it. Every atom on Earth is pulling on every atom of you. You're also pulling on it. How do you pull if you don't have a mediator? What are you going to pull with? Are you going to throw stones, discrete stones, at the thing that you're pulling? Are you going to do it with field, with energy, with mass? Are you going to do it with concepts? It says you're pulling on atoms right now on the other side of the Earth. Okay? So the only way you can imagine pull is if you have an object, if you have a thing. So there's got to be something that we can't see here, something that we can't see here, whether pushing or pulling, right? That is attracting this to the Earth. Why doesn't it go to the moon? Why doesn't it go to Jupiter? Why doesn't it go into outer space? Something obviously is pulling on this, okay? Some people say it's push, but everybody really defines or has this notion that gravity is a pull force. And Muller's telling you it's every atom on Earth is pulling on every atom of you, on every atom of the scroll. So you got to think about that for a moment, because apparently there's something that's pulling that we cannot see or touch. And yes, an object is not that which you can see or touch. What was it? An object is that which has shape. Not all objects, not all shapes, right, can be seen or touched. Among them, the air. In fact, here we have, for those of you who need authority to change your minds, here we have Brian Green. He's going to tell it to you in your face, okay, so that you understand it well. Okay, here it is. Listen to him carefully.
We are surrounded, right, by physical substances that we know to be real, right, but which to the naked eye are invisible, right? Air, of course, but, yet more elusive examples are X-rays and radio waves and infrared rays. These are elements of the electromagnetic spectrum that are outside the sensitivity of our eyes. Of course, since, I guess it was around 2015, we have learned that we are also immersed in a sea of incredibly weak gravitational waves. So here's the thing. When we look out into the cosmos, we should perhaps anticipate that at least some of what's there might also be invisible, not just to the naked eye, but perhaps also to our most refined equipment.
Okay, so there are things that we cannot see or touch, and they form these objects, these things that bind any two atoms. Okay, and so what we propose is, on this side at least, is this. We have the electromagnetic wave, which is a concept, a mathematical concept, bunch of vectors. Okay, magnitude and direction. That's what they say these fields are. Field is just a bunch of numbers, value at each point in space. None of those are physical objects. Those are all concepts, and we're replacing that concept that came up with people like Augustin Fresnel and James Maxwell, and we're replacing it with a rope. They've been mistaking a rope for a wave, a transverse wave. Okay, rope is a physical object. A thread, it's made of two threads. A thread is a physical object. A field is not. Field is a concept, okay? And whereas the electromagnetic wave goes one way and off to nowhere, the rope binds any two atoms, like Richard Muller said, pulls on one atom, pulls on another. Now you have a physical entity that can pull on another atom, okay? So now we are in line with what he said. And while it pulls, it also torques. And by torquing, you have light and gravity in a single mechanism, in a single cause, right? Single object. We have the theory of everything right there in front of me. And here you have this in motion. You have the quantum mechanics version, which is that ridiculous atom that cannot explain why the bead does not fall towards the center, you have the negative bead. It doesn't fall to the positive nucleus, in this case the proton, right? And when it falls and rises, somehow it emits this abstraction, which is a gravitational wave, right? Whatever that is, it goes off to nowhere. And that contrasts with our model, which is two atoms bound by a rope, a pair of twine threads. And as it expands and contracts, you can see why it torques the rope. The torsion along the rope is what we call light, and the expansion and contraction is what we call the quantum jump. That's why, the little bead goes from one energy level to another. It's pumping back and forth. They're talking about a membrane, which they confuse for this bead that's jumping between energy levels or orbitals or whatever they want to call them, okay, which are all concepts. Here we have objects, okay? And so there's the difference between two models. In the case of gravity, because the same model explains gravity, here you have the version that they have, which is two black holes, and because they move around each other, they create these gravitational waves in what they call space-time. That space-time, the lines that you see there, those are number lines. That's what they are. It's not a fishnet. Okay, it's not a canvas like they illustrate there. No, they're talking about number lines. So they're not physical entities. They're mathematical concepts which they're turning into physical objects, bending them, running waves through them, which is all irrational because they're talking about mathematical concepts again. And then they have these two black holes, which are zero-dimensional, according to their definition. They have singularities at their centers and surrounded by concepts known as the event horizons. And so all you see there are a bunch of concepts which they've illustrated. They've illustrated the black hole, which is a concept, and they create gravitational waves, which are concepts, along a space-time, which is also a concept. All just number lines. And so that's their version, and we have a rational version because we're saying every atom is connected to all others. Every atom of the astronaut is connected to every atom on Earth, and therefore as he falls, the ropes that interconnect every one of these atoms fan out. And by fanning out, you have more and more ropes tugging on a separate axis. They have different angles now. They were superimposed before. Now they're not superimposed anymore. And so because of that, you see the acceleration of gravity. That's what gravity is. So we have a physical interpretation. We have a rational version of it, whereas mathematical physics does not. Do you believe in the rope model? Do you believe that that's how gravity works? Do you believe that that's like how light works? We don't care. Science doesn't care. Science doesn't care if you believe or not. Belief is part of religion. We explain so that you understand. If you understood, we finished with science. What continues now is religion, belief. Whether you're convinced or not. That's something else. Okay, so last couple of weeks, what we did, we first did objects, and then we went into some of the other concepts that we need to lay the foundations of physics, okay? And one of them, the first one after object, is distance. Okay, so here we have distance, the foundation of physics. It includes, that you need an object, but now you need also distance, and that's related to space. It's the separation between two objects. That's the qualitative notion of what distance is, okay? It's not what it is in mathematics. In mathematics, distance is distance traveled. It's a movie. Distance here is a photograph. It's separation. Okay? Separation is a static concept. Distance traveled, that's not a static concept. You need several frames of the movie to understand distance traveled because you're unrolling the tip of the measuring tape. Okay? And here it is. Okay? This is the definition they have for distance in the religion of mathematics, mathematical physics. Here it is. This is out of Wikipedia. Distance is what? A numerical measurement of how far apart something is, right? Points are or whatever. Yeah, what they're doing is they're unrolling the measuring tape. And then here in physics, distance may refer to what? A length. They're saying that length is distance. And we have a problem there because there you see it at the bottom. Distance is what's between objects. It's the space between objects. You're unrolling the measuring tape from surface to surface of two objects, but you're unrolling the measuring tape through space, through nothingness, right? So distance is what separates two objects. Or like I like to say, distance is what lies between lengths. What is length? Length is the continuous matter of an object from surface to surface. That's what length is. Distance is not, the separation, the continuous matter between the surfaces of an object. No, it's the separation between two objects. Okay, so we have a difference in between distance and distance traveled. And so, in order to show or to explain these concepts, I had to invent what I call this tool, the universal movie. Here it is, okay? The universal movie is every atom in the universe in a single frame, okay? If you want to see motion, you need, or any of the dynamic concept that you see at the bottom, you need to have at least 2 frames of the movie. Whereas for the upper ones, the ones in yellow there, they fit in a single frame because they're static concepts, and you do not need to have 2 frames of the movie to understand them. They're defined as static concepts. The ones at the bottom are all defined as dynamic concepts. You need 2 frames of the movie. And so here we have good old Father Universe. That's what he looks like. Okay. What is Father Universe? It's every atom in the universe, and it only has what you see at the top: distance, location, and existence. That's all it has. Okay. Every atom in the universe just has location, distance from all others. And that's what Father Universe is. Okay. Do the other frames bother you? Okay, let's put them in a single frame. There you see it. So that's Father Universe. Single frame. We don't need many frames to conceptualize Father Universe. Father Universe is just every atom in the universe that comprises the universe. Okay? And so what these people have is distance traveled. They don't have distance. What they have is they need, for distance traveled, they need 2 frames of the movie at least. Whereas for distance, all you need is separation. You can conceptualize distance in a single frame. Okay, so distance traveled is not the same thing as distance. Distance belongs to physics, qualitative separation. And distance traveled, which is a quantitative concept, belongs to math. It's an itinerary, a trajectory. Okay, so let's distinguish between those. Okay, and then we moved on to what we call location. Okay, here it is. Foundations of physics. Location, what is it? The set of distances from one atom to all others in the universe. Okay. Here we have it in the universal movie. Okay. Here you have good old God, and he's got distance separation, right? With respect to a cube, the earth, a cylinder, whatever. Every atom in the universe, if you will, right? So all we have is distance, separation. Okay. Here we have it in a single frame. If God wants to, be in we don't need a movie to conceptualize distance of God or every atom of God with respect to every atom in the universe. And we don't need that. And here we have good old God. If you want him to exist, he simply has to have location. And there he is. The definition here, physical presence. That's what it is, an object that has location. You get rid of this one. And all you have is existence. If you want to exist, all you have to have is a body, a thing, something that has shape, right? That which has shape. And it has to, in addition, have location. Okay? And so here we have good old God. If God wants to exist, it's very simple for him. All he's got to do is have distance, shown by all those lines, with respect to every atom in the universe. So what you're saying when you say, let us assume that God exists, what you're saying is, let us assume God is a physical object, an object, right? And God has distance with respect to every atom in the universe. That's what you mean by exist. That's what you're saying when you say that God exists. And when you say God doesn't exist, you're saying that God is either a concept or that God does not have location within the universe, meaning distance with respect to every atom in the universe. Okay, so we can talk about the existence of God or the non-existence of God in a rational way. We just have to define what we mean by exist. Exist is an object that has location. We're done, period. Punto. Punto final. Okay, so what is motion? I mean, we've got object, we have distance, location, existence, right? What is motion? The first dynamic concept that we're going to analyze, okay? Does Father Universe move? Well, Father Universe looks at himself and every atom just is there. That's it. It doesn't move. It just there, has location. He looks at himself, then goes to sleep for 1 billion years or 1 trillion years for an eternity. Then he wakes up and he looks at himself again. He says, all I have is location. Because he doesn't have memory. He doesn't remember his previous location. We humans, we living entities, we remember previous location. We have this thing in this recording device in our heads, and we record the previous location, the previous one. We say, oh, it's moved. But see, Father Universe only has, every atom only has location. Looks at himself and says, I only have location. Okay? And so what is motion? So let's go with the gurus. Let's go to good old Newton. He's the first guy who, I guess, or one of the first guys to attempt to define motion, right? Scientifically. And he said, I do not define motion as being well known to all. Okay, so he came up with the 3 laws of motion. And he says, the first thing I'm going to do is not define motion. Okay, so that explains why you came up with the 3 laws. In fact, he did not come up with the 3 laws. The laws already, so-called laws, already were put out by people like Descartes and Galileo. They already had the same laws that Newton talked about. He just put them in 3 nice little phrases and they gave him the credit. But, these laws already were known and they were put on paper also. Okay? Look up the Wikipedia says, what is motion? And I love the fact that, they said the action or process. So they're already using words that are dynamic, that embody dynamism. They have dynamic embodiment in them, like action and process, and moving, changing, and movement, even position, because position in mathematics, right? In the religion of mathematics, what is position? It's how you get to the treasure chest, not where it's at. You have these ordered pairs or ordered triplets, and what they are itineraries. How many steps to the right, how many steps north to reach the treasure chest. So position is not a static concept, it's a dynamic concept represented by an ordered pair or triplet or whatever. And it says motion is when an object changes. The word change, look up change, it involves motion. Position, again, an itinerary. Given time is built of motion. You need to define motion before you define time. They're using time to define motion. So we have all these contradictions, all these irrationalities. Okay, and yeah, Newton did not do a good job, so I don't think we can credit him with having defined motion or the 3 laws of motion, because he never knew what motion was. He never defined it. He specifically said, I'm not going to define motion because we all know what that is. What's the purpose of that, right? Okay, so you look it up in the dictionary. What is motion according to the dictionary today, right? And it says, motion, the action or process of moving or being moved. Oh, great. So motion is moving or being moved. Oh, we learned a lot. Motion is moved and moving. And you look it up in Merriam-Webster, says motion, an act. What's act and action? What is an action? Motion. Or instance of what? Changing. What is changing? Again, motion, movement. And so we have a problem because they're using synonyms or words that are founded upon motion to define motion. All these are irrational definitions. In fact, my recommendation is never look up a word in the dictionary if you're going to use it in science. Okay? That's the way it is. And then you have the definitions of action, of process, of moving, of movement, of change, and they all involve one of the others. So all they have is synonyms. They never define what motion is. You know, what is action? A process. What is process? An action. What is moving? Movement, or capable of motion. What is motion? It's the word we're trying to define. What is change? Making something different from a different place or whatever. So all these words involve motion. You can't use any of those words to define motion. If you do, you don't have a definition of motion. What you have is a synonym, and synonym is a circular definition. No definition at all. Okay? Can't use synonyms or antonyms for that matter. Okay. Okay, so here we have the bot. We asked the bot, look it up. And we have all these R2D2s that they've created. Again, all this comes from mathematical physics, so keep that in mind. You won't find an objective answer. You'll find a subjective answer of mathematical physics. So if you look up the word motion, this is what you'll find. It says motion is when an object changes, right? And talks about time. That was from Wikipedia. Look up change, you look up time, and it turns out they involve motion. Okay? You go to the Eric Weinstein, the Wolfram World of Physics, they have no definition of the word motion. They already start with types of motion. And the same thing for Stanford Encyclopedia of Philosophy. I mean, if they send you to a philosopher and say, hey, go find out from the philosophers what you mean by motion, they have no definition either for the word motion. And hyperphysics, one prominent site of physics, right? They also go into different types of motion, and they just say motion is described in terms of displacement, time, velocity, and acceleration. So they already have things in motion to define motion. Okay? Displacement is motion, time is motion, velocity is motion, acceleration is motion. So they haven't defined the word motion. And the bot, he tells you, they're right in your face. It's the change in position of an object over time. What is change? What is time? Well, we already covered that. It's motion. So we have no idea what motion is from any of these people. No one in mathematical physics knows what motion is, can tell you what motion is. And just in case, people say, well, maybe some philosopher did that in the past. And we go to Ayn Rand, and she tells us what motion is, perfectly defined. It says, motion presupposes the thing which moves. I love that. Without the concept of entity, there can be no such concept as motion. So she's saying in the first two lines there that for motion, you need an object. Okay, great. Then she said, change exists. No, change does not exist. Change is a concept, so change cannot exist, meaning she had no idea what the word exist means because she applied it to a concept. When a thing is changing, that is what it is doing. What is still is still. What is in process is in process. Oh, great. Then she says, but a moving object is not at any one place. If it is moving, it is not at a fixed position. That sounds a lot like Heisenberg's uncertainty principle, principle of indeterminacy. Said, when the ball moves, it doesn't stand still. When it stands still, it doesn't move. That's what he got his Nobel Prize for proving that ball that stands still doesn't move. Great. And so, these people had no idea what motion is. And some people might criticize me and say, Bill, why are you making fun of poor old Ayn Rand? Yeah, I make fun of her because a lot of people say, hey, you said the same thing as Ayn Rand. Or Wittgenstein, or any of those, David Hume or Immanuel Kant, right? No, none of those people have said anything that I said. If you confuse me with them, you have no idea what I'm talking about. You still don't understand. No, these people never defined the word object. They never defined the word distance. Therefore, they knew nothing about location, which is founded on the word distance. And if you don't have location, you cannot define the word existence, let alone the word motion. So these people had no idea what motion, existence, location, distance, or object are. We have totally different definitions of these words. We set the foundations of physics. That's what we're doing. So when people confuse me with Ayn Rand or the electric universe, which thinks that plasma is a physical object or that ether is a physical object or that electricity is a physical object, I have to clarify and make fun of them so that you realize that, no, we are not saying the same thing. You simply did not understand so far, okay? Okay, so here we have the foundations. What is motion? Foundations of physics. Motion is two locations of an object. You have to have at least two locations. Here it is in the universal movie, okay? You look at an object, in this case, some kind of box, square, cube, whatever you want to put in there. And in the second frame, you see it in a different location. That's what motion is. That's how we define motion. Two locations requires two frames, okay? And so with this, you destroy at least special relativity, if not all of general relativity as well, all of relativity. You say, why, Bill? Well, because, see, these people talk about going to the past or going to the future. And people like the past more than the future. Some people talk about going to the future, but people like to go to the past because we're more familiar with the past, with our history. And we say, hey, I'd like to be in the days of the Vikings or the days of the Aztecs or whatever. And say, I'd love to travel. And they've made lots of movies of time travel. It's almost always to the past. Okay, in general terms, it's to the past, because we're more aware of that, right? And so they say, hey, can you travel to the past? Well, most mathematicians say not to the past, but you can to the future for whatever reason. We don't care, right? But that's what they say. But let's look at the traveling to the past, right? It doesn't change our argument whether you go to the future or the past, but people, again, love to go to the past more than they like to go to the future. The question is whether you can go and see Napoleon or, Julius Caesar or Alexander the Great. Can you be there with Alexander the Great and shake hands with him? And Father Universe, destroys that notion. Says, no, that's impossible. And why? Because he has no memory. See, he doesn't have a filing cabinet where you can go to the frame where all the atoms are still there, right? In the present tense, are still there, and you can land on that frame where the Earth was like it was, thousands of years ago, or millions of years ago, or billions of years ago, that you can land there and you find the same atoms that we have today in a different location. Okay, so time travel requires that Father Universe keep, that frame of the movie. And here you have Brian Greene, and he does give you an idea of what I'm talking about here. He uses time, right? He says they have all these time slices, and all you have to do is go to one of those slices. Like if Father Universe makes clones of himself, of every atom that he's made of, in every location. So it's not like he's moving, he's creating clones at a new location. That's what these people are saying. And here it is, good old Brian Greene. Listen to him. Well, it's just to see it. Okay, here it is. You see all these time slices that make up space-time, right? And he's got all these slices. He's got to cut them into slices. He's going to show you that, you have all these slices, that the universe is made of this block universe, the whole block, the whole loaf of bread. Okay? So what's the issue? The issue is these people say that you can go to one of those slices. And for that, Father Universe would have to make a clone of each slice at new locations as you go along. Okay, so you don't have the atom at a new location at a different frame. What you have is the second frame is a clone of the first one, but every atom is just a little at a different spacing than it was before. That's all it is. So these people are saying with special relativity that you're creating new atoms. You're cloning every atom in the universe at every frame of the universal movie. And that's obviously irrational. I mean, if you want to believe it, yeah, that's religion. But it's irrational as an explanation. Okay, so just want to make sure that you understand that this tool called the universal movie, Father Universe only has location. He does not have motion. Motion is what we see when we watch the movie of every atom moving, because we have this recording device called the mind, thought, consciousness, whatever you want to call it, right? Spirit, in our brain. So we record previous locations and that stays in our memory, and we're recording all along, right? We're recording all along. We're recording the whole thing. We say, hey, that lion, it moved from here to there. Not according to Father Universe. Father Universe only looks, wakes up after gazillions of years, and says all the atoms of that lion are at a given location with respect to all others. There is no motion as far as Father Universe is concerned. But we entities who have recording devices in our brains, at least for a short time, right? And we remember all these locations. We say, oh, the lion moved. Okay? So keep that in mind when you're analyzing location and time, and motion and time as well, right? Yeah, there is no time as far as Father Universe is concerned. That destroys the religion of special relativity, which is founded upon time, upon the fact that if the speed of light is fixed, it's a constant. What varies is time. And that's they prove that with an equation. Okay? We don't do that in physics. In physics, we look at reality. What exists is a static concept because it's an object plus location. Okay? Okay, let me go with a couple questions a fellow asked, and they were, I think, important questions, so I'd like to address them. Okay, and maybe you learned something today. Who knows? Okay, he first asked the following. He says, why did you call the electric thread the one that goes through the center instead of the one that forms the electron shell? Okay, so if you look at the atom there, my atom, the atom of the rope model, you see that the electron shell is made of magnetic threads. And he's saying, why didn't you name that one the electric thread and the one that goes through to the proton through the center of the atom, the magnetic thread? And my first answer is it was arbitrary. Okay? Now, this happened 26 years ago, long time ago. Please, have pity on me, okay? I'm 72 years old. The other day turned to 72, so, I can't remember all this stuff. But all I can tell you is, yeah, it was arbitrary as a first instance. But then there was a reason for it, and the reason is as follows. You can see the electric thread, the magnetic thread are made, one is blue, the other one is red, but really it's all the same thread. There's no difference between those two threads. I color-coded them so that you can see, you can contrast them. That's it. That's the only purpose of color coding. But it's the same thread. Okay, so there's a single thread in all of the universe. Okay, so what's the issue? The issue is when you have magnetism, right? Here you have a magnet, two magnets, and we see nothing in between here, right? But there is something in between there, or like good old James Maxwell said, there's matter in motion in that region we call magnetic field. Yeah, there's something in motion. We're saying what's moving there is the thread. It comes out of the rope, right? Starts moving around. So the original thought I had was that one thread comes out, and that one's going to do the magnetism, the clash in the case of repulsion. And if they go in the same direction, we have the attraction mechanism. And it was done with this thread. And I said, well, if one thread comes out and starts moving around, we'll call that the magnetic thread because that's producing magnetism. That was the context, okay? My son came around, Hans, and he said, you're wrong. Okay? Maybe both threads come out, and they both start swinging around. And so he killed me with that. I think he's right. I think both threads come out. That's one issue. The other one is that another thread that comes out is the one that makes the electron shell. Okay? So the electron shell, if it's spinning, maybe those threads come out as well. So whether it's the one coming out of the electron shell or from the rope itself, that's something theorists will have to look at and find out which one they think is doing it. But, the magnetic threads that spin around could come out of the electron shell or from the magnetic thread, in which case magnetic is probably the correct word because that's the one that's going to be doing the magnetism. Okay, and that's the context. Okay, so nothing more than that. Otherwise, it was just arbitrary. Okay, but that's, I think, what happened. 26 years ago, okay? I think it's the same fellow, and he asked the following. He says, if the rope is torquing, what is happening to the magnetic thread? Okay? Does it go around the shell like a person skipping rope, right? Is it moving or around it? It's building the shell, the electron shell, the membrane that encapsulates the proton star. Is that thread moving around? Okay? And that's one question. The other one is whirling in situ as well as it goes around. So we have two motions. One is the spinning in situ, spinning of the thread, as well as the spinning or the rotation around the electron shell. Okay, we have a couple motions that we have to look at here. Okay, I can imagine an electron thread twirling in situ because it's straight, but I'm not sure how to picture what happens with a magnetic one, assuming the rope is not moving along its length. And by that I mean the rope reeling in thread from one atom and into the next. Okay, so there's several questions that he's asking at the same time, so I just want to put it in the right context. Okay, let's find out what we're talking about. And here, one of the first things you have to look at is what I call the ionic bond. What is ionization? And if you go to quantum mechanics, ionization means that the electron bead is leaving the atom, leaving the atom as a positive ion, right? The electron, which is a negative particle, leaves the atom, and so now the atom that remains behind is positive, and it wants an electron back. Okay, so that's the notion quantum has. The problem with that is that they have an irrational atom to begin with, which is Niels Bohr and Ernst Rutherford's atom, which is the little bead circling a little bowling ball called the proton. And what they cannot justify in that model is why the electron bead, which is negative, doesn't fall directly to the proton, positive proton, or why it doesn't spontaneously leave the atom. So until they can answer that, they have an irrational atom. They cannot make that assumption because the assumption is not justified by what you're staring at. The electron does not leave, the electron does not fall. We have a problem with that. In fact, that's how quantum was investigated to begin with. Why doesn't the electron fall into the nucleus? That was the question, and to this day, no one has answered that question. So quantum mechanics is based on a question that no one's ever answered in the last 100 plus years. That's where we stand on quantum mechanics, okay? And so that's the version of quantum mechanics. Here's our version of the ionic bond, okay? And what you have here is that you have the threads moving around the surface of the electron shell. In other words, the electron shell has a surface, and every thread is moving around it. When two atoms come together, like in this case, an s orbital with a p orbital, the one on the right, the bluish one there, the purple one. When you have that situation, you can see what's happening with the threads. One thread, they're both moving in a clockwise direction in this case, in this example. And because of that, you have attraction. You have the ones from the blue coming up while the ones from the yellow are coming down. And that's the positive negative version of quantum mechanics there illustrated for you. If they were going in opposite directions, they would not come close to each other. And obviously we have a version of that as well, which is the gears. Here are the gears, okay? So you've probably seen this. You know, when you have them going in opposite direction, right? They don't like each other, okay? They don't like each other, so they're going to tend to push each other away. On the other hand, when you have them going in the same direction, we have a stop, full stop. Why? Because, you know, one's coming down when the other one's coming up, and, you know, they pull on each other, they pull or push on each other, right? And so there's no motion, okay? And this is going to be important for another question, and that is why? You know, why it is that when you have the rope, you have two threads, right? Why don't they blend? If, you know, here, let me show you with an example. Here you have paper tissue, right? And I'm going to twist it and turn it into a thread. Think of that as a thread, okay? And what happens with this? Well, it's tangled around another thread, right? This is our rope model. Let me see if I can twirl them around each other. Okay, here it is. Okay, so this is our rope, right? They're once twirled around each other. And the question is, why don't they blend if threads do not touch each other? Well, you can see that first they're twirling in opposite directions. Okay, one is clockwise, the other counterclockwise if you see them from either end. That's one issue. The other one is if you have these going against each other, like at great speeds, these two paper tissues or cotton swab, those cotton pieces, right? They would go right through each other and they would cut across each other. Okay, one would cut or both of them would cut when you go at great speeds, 90 degrees to each other. But here they're pulling that direction in opposite in the lengthwise direction. That's one issue, and the other one is that they're moving in opposite directions. Okay, each thread is moving in opposite directions. And then you have the situation of the gears where you have, they're doing this. So they don't like each other. And so they don't blend because first there's no speed in that direction. The speed is in, the forward direction, the lengthwise direction, not in the widthwise direction, right? Then they're moving in opposite directions. So that's why they don't blend. Okay, that's my answer to that. That's my theory. Okay, and what happens when they go into the atom? Okay, and here it is. You have the Pauli exclusion principle. What is that? The answer from quantum mechanics is no two identical fermions, right, can occupy the same quantum state at the same time. Photons can exist in the same place at the same time because they're bosons. They overlap. Photons are bosons, right? Just like all the mathematicians, a bunch of bosons. They're force carriers, and those bosons are force carriers in the religion of quantum mechanics. In an orbital, a maximum of 2 electrons can occupy the same space, and the 2 electrons must have what? Opposite spins. That's the critical point from Pauli's exclusion principle. And so what are we talking about? We're saying one is clockwise, the other one is counterclockwise, because they're talking about spin, which they never define, but that's what they're insinuating. Under the rope model, it's very clear why that's the case. If you have the threads spinning all along the surface of the electron shell, when you go to the opposite side, hopefully that one is clockwise and this one is counterclockwise. In other words, they have opposite spins. Okay, they must have, because that's simply physics. If you take that counterclockwise all the way around, you're going to end up with clockwise. Okay, so we can explain Pauli's exclusion principle very easy with the rope model, with the thread model. They're spinning all around the electron shell, and the reason that two threads do not blend, during in the case of the rope, right? Why doesn't the blue blend with the yellow if they don't touch each other? Well, again, each thread is twirling, spinning in situ in opposite direction. That's one issue. The other one is the pull is in that direction, the tug. The tension is in that direction, not in the widthwise direction, right? And then there's no speed in the widthwise direction. If one thread came across another in a perpendicular direction at great speeds, it would go right through each other with a very tiny friction. There is a friction, that's what creates magnetism, but only in that case can you have a thread go through another or a rope go through another. Not in the lengthwise direction. That's the explanation I have for that. Okay, take it or leave it. And then this fellow asks another question. He said, how do nukes work in the rope model? Is it just a release of thread from broken atoms? Okay, well, we have the same explanation that quantum has here. In other words, we have a chain reaction of atoms and neutrons, right? So there's this chain reaction. One hits the other and just breaks it up, and then the other one breaks up, and the other one breaks up. But where we differ is in that word energy. There's no such thing as energy in physics. Okay? Energy is a mathematical concept, a quantitative concept. Okay? So we don't have an energy. What is energy? Well, energy is, the signal, the disturbance propagating along the rope, which it's not propagating at all. What it's doing is twirling in situ, and what we have is this thingy, which we call a signal, whatever you want to call it, a wave, right? That's somehow going from A to B. Okay, it's propagating along the torsion, right? And we feel it only when it touches the atom. That's where it twists right at the surface of the atom, and that's what we feel as light or as energy or whatever you want to call it. Okay? And so the difference is that when there's a nuclear explosion, right, or you have fission or fusion, really, it doesn't really matter. What you have is a torsion of the rope. You have a torsion of the rope at great speeds, right? So you have great frequency, very short wave length, right? And that's propagating along the rope. Just goes through the rope to the next atom, to the next atom, to the next atom, and so on down the line. So that's the energy portion of a nuclear explosion. Okay, so we have to look at that in a new context now with the rope model. And here, let me show you another issue related to the nuclear explosion that you want to keep in mind. Okay, and I'm going to do it with tritium. Okay, but really it applies to uranium, which is what they use in the nuclear bombs, in the nuclear explosions, right? In these atomic bombs, these atomic weapons or hydrogen bombs or whatever. Why is uranium radioactive? Why is tritium radioactive? Tritium is hydrogen. You know, if you put another neutron in there, you have deuterium, and if you put a second neutron, now you have tritium. And so, why is tritium radioactive? You know, and that's the question you need to have answer when you're doing when you're looking at radioactivity, which is an important part of nuclear weapons. And so here it is. Let me show you what I'm talking about when I talk about radioactivity. Okay, here it is. What you have here is
when the electron shell of hydrogen expands, it incorporates an adjacent neutron
right?
and becomes
and
deuterium.
That's a long story, but
if the shell expands again, it now incorporates a second neutron and becomes tritium. The reason tritium is unstable and radioactive is that the balloon is stretched to the limit. The more the outer shell is stretched, the more unstable and radioactive an atom will tend to be. It will attempt to expel nuclides.
Right? And hydrogen wants nothing more than to get rid of them and go back to its normal state. So
when the electron shell of hydrogen expands, it incorporates an adjacent neutron and becomes deuterium. If the shell expands again, it now incorporates a second neutron and becomes tritium. The reason tritium is unstable and radioactive is that the balloon is stretched to the limit. The more the outer shell is stretched, the more unstable and radioactive an atom will tend to be. It will attempt to expel nuclides.
Not only radioactivity, but why deuterium and tritium both are unstable. Because you have an expansion of the electron shell, and the electron shell does not like to be expanded so much. It's stretched to the limit. It's pulling all the thread to make that expansion from every atom in the universe. And so it likes to squeeze those neutrons out of there. And that's the reason for the instability we call radioactivity. And that's also part of the atomic weapon or nuclear processes that you have to be able to answer. Okay? So with that, I hope you have some food for thought, and we'll see you with that next week.